For the purpose of this project, we are going to test the differences between a non-fluted and a fluted barrels of an AR-15 rifle, and to test and understand the heat dissipation of the fluting of the barrel compared to a non-fluting. And for this experiment and our purposes, we are only going to be testing a non-fluted barrel and a fluted barrel. The fluting of the barrel has two purposes. The first purpose is to decrease the weight of the barrel without sacrificing a great deal of accuracy and precision, and the second is to allow the barrel to cool quicker after it has been fired.
For our experiment, 3 different barrel profiles were evaluated. The first was the non-fluted barrel. The 2 tests conducted on this barrel were a physical experiment where a full magazine, or 30 rounds, were fired rapidly through the gun, and the barrel's temperature, as well as the ambient temperature, were recorded. In order to find the heat transfer coefficient, we measured the time required to cool from 60 degrees Celsius to 30 degrees Celsius. A CFD model was then conducted to compare the results of the physical test. The boundary conditions were set based on the results of the physical test, and once these boundary conditions were deemed appropriate, the fluted barrel tests were then conducted under these same boundary conditions in the CFD program. And this was done in order to compare how the heat would dissipate through the non-fluted barrels, or through the fluted barrels compared to the non-fluted barrel.
So some of the equipment that was used, as stated before, we used a thermocouple on an AR-15 rifle with the non-fluted barrel. The thermocouple was taped to the end of the barrel, while one end was out recording the ambient temperature. In the physical experiment, we shot a full magazine of 30 rounds, and that was rapidly shot. And after that was shot, we took the temperature difference over the time to be able to record and understand the heat transfer that was going through. After we used those recordings and those temperature differences to record the heat transfer coefficient, we got around 33 watts per meter squared Kelvin. After the physical experiment was concluded and the numbers were recorded, a CFD experiment was then conducted on a non-fluted barrel to compare the results. Here we have a recording of how the heat dissipates through the barrel. As you see over time, the dissipation grows larger and larger. And on the top right here, and on the bottom right, there are 2 mesh pictures of the non-fluted barrel of how that reacts.
So here's a CFD test of the barrel that has the 4 flutes. This test was conducted under the same boundary conditions as the non-fluted barrel, and it looks a little something like this. You'll notice that the temperature profile seems to act a little bit more erratically. This could be due to the tripping of the boundary layer because of the fluting, which would also result in a greater rate of heat dissipation. The pictures at the right of the video are the meshes that were generated for the test in the CFD program. The mesh looks a little bit different than the previous case did. That's just mostly due to the geometry. The grading is slightly different as well, which we won't really get into at this point. And here's the CFD case that was done on the 8 fluted barrel. This one turned out a little bit different, as we'll see here in just a second. The temperature profile doesn't seem to be flowing the way that we would have hoped it to, namely upward. It ended up flowing downward for some unknown reasons. The mesh is also pretty different in a lot of ways, also due to the geometry as well as the mesh grading itself. So here's the final results of our testing in the CFD models. The non-fluted barrel yielded a heat transfer coefficient of 33 watts per meter squared Kelvin. The case where there were 4 flutes yielded a heat transfer coefficient slightly larger than that at 33.4 watts per meter squared Kelvin. And the 8 flutes yielded a heat transfer coefficient of 147.8 watts per meter squared Kelvin. One of these things is obviously not like the other. The 8 flute test was flawed, which is why the heat transfer coefficient is such a large number. However, we do notice that there is an upward trend regarding the heat transfer coefficient versus the number of flutes that are in the barrel. So overall, what we can learn from this is if we can increase the number of flutes in a rifle barrel, it not only lightens the weight of the barrel itself, but it also increases the heat transfer coefficient of the barrel, allowing it to dissipate heat quicker.